Right now, somewhere above your head, an invisible shield is keeping you alive. Earth's magnetic field stretches 40,000 miles into space, turning aside a relentless storm of radiation that would tear apart your DNA within hours. Step beyond it, and you enter a universe that begins dismantling every system your body depends on, not all at once, but in layers. First, the atmosphere disappears. Then the magnetic protection fades. Then sunlight weakens until the sun becomes just another point of light among billions. Communication delays stretch from seconds to minutes to hours to days. Even the solar wind, the last breath of our star reaching outward into the dark, eventually thins to nothing. And you cross into a space where no human signal, no rescue mission, no supply chain can ever reach you. Now settle in and get comfortable. Let's begin. You have probably seen the photographs. An astronaut floating inside the International Space Station. Sunlight streaming through the cupola windows. Earth curving softly below in sweeping bands of blue and white. It looks peaceful. It looks safe. The astronaut smiles, spins a water droplet in midair, and the whole scene carries the quiet suggestion that space is simply another place humans have learned to live. That suggestion is a lie. Not because the International Space Station is dangerous, although it is, but because it creates an illusion so convincing that almost no one looks past it. The station orbits roughly 250 miles above the surface. At that altitude, you are technically in space. You experience microgravity. You see the blackness beyond the atmosphere. You can watch 16 sunrises every 24 hours as the station races around the planet at 17,000 miles per hour. But you are not deep in space. You are barely past the front door. The reason that distinction matters is something most people never think about. Because most people have never been told what is actually keeping them alive up there. It is not the station walls. The aluminum hull of the International Space Station is far too thin to stop the most dangerous particles flying through the solar system. It is not the air supply, though without it, you would be dead in minutes. It is not the solar panels or the water recyclers or the food shipments that arrive every few weeks from Earth. All of those systems are essential, but none of them is the primary reason astronauts survive in low Earth orbit. The primary reason is something much larger, much older, and completely invisible. It is Earth's magnetic field, and it is the first protection you lose when you venture deeper into space. The magnetosphere is not a wall. It is not a dome. It is a vast, turbulent, three-dimensional structure generated by convection currents of molten iron churning in Earth's outer core thousands of kilometers beneath your feet. This dynamo process creates a magnetic field that extends tens of thousands of kilometers into space, forming a bubble around the planet that deflects the majority of charged particles streaming toward us from the sun and from beyond the solar system. On the sunward side, the magnetosphere is compressed by the solar wind to a boundary roughly 40,000 miles out. On the night side, it stretches into a long, trailing tail that can reach past the orbit of the moon. The shape is not symmetrical. It is not stable. It flexes and ripples and deforms in response to changes in solar activity, sometimes ballooning outward during quiet periods, sometimes being shoved inward during intense solar storms. But even at its most compressed, it wraps around the planet like an enormous, invisible cocoon. And everything inside it receives a level of radiation protection that nothing outside it can match. What the magnetosphere actually does is redirect. When a proton or a heavier ion comes screaming in from a solar flare at several million kilometers per hour, it carries an electric charge. That charge means it responds to magnetic fields. Earth's field grabs these particles and forces them to spiral along magnetic field lines rather than punching straight through to the surface. Most get deflected outward, swept around the magnetosphere, and carried away by the solar wind. Some get trapped. Those trapped particles accumulate in two donut-shaped regions wrapped around the planet called the Van Allen radiation belts, named after physicist James Van Allen, whose instruments aboard the Explorer 1 satellite detected them in 1958. The inner belt sits between roughly 600 and 3,700 miles above the surface and contains mostly high-energy protons. The outer belt extends from about 8,000 to 37,000 miles and holds mainly high-energy electrons. Together they form a zone of concentrated radiation that spacecraft must either avoid or pass through quickly. The International Space Station orbits well below the inner belt, skimming beneath the most dangerous region. It still receives some radiation, roughly 1 millisievert per May, significantly higher than what you absorb on the ground, but manageable for missions lasting 6 months to a year. Astronauts on the station accumulate radiation doses comparable to a few chest X-rays every day. Elevated, but survivable. Here is what most people do not realize. The station is not protected primarily by its own shielding. It is protected by where it is, 250 miles up, still tucked inside the magnetosphere, beneath the Van Allen belts, bathed in a magnetic field strong enough to turn aside the bulk of incoming charged particles. The station's aluminum walls provide some additional protection, roughly equivalent to a few centimeters of shielding. But against the highest energy galactic cosmic rays, iron nuclei traveling at nearly the speed of light, those walls are almost meaningless. A single such nucleus can punch through meters of material. What stops most of those particles from reaching the crew is not engineering. It is the planet's magnetic architecture. When you leave that architecture behind, the radiation environment changes in ways that no spacecraft hull currently built can fully compensate for. This is the first threshold. Not a line drawn on a map. Not a sign that says you are now leaving the safe zone. It is a gradient, a fading, a slow withdrawal of magnetic influence that begins the moment you climb above low Earth orbit and accelerates as you move outward toward the Moon. The magnetic field does not vanish instantly. It weakens. At geostationary orbit, about 22,000 miles up, the field strength has dropped considerably compared to the surface. At the outer edge of the Van Allen belts, it is weaker still. And by the time you reach the vicinity of the Moon, roughly 239,000 miles away, Earth's magnetic influence has become so faint that it offers almost no practical protection against incoming radiation. But even that description is too simple, because recent research has revealed something more complex happening in the space between Earth and the Moon. A study published in Science Advances analyzed data from multiple spacecraft and found evidence of a galactic cosmic ray cavity in cislunar space, a region where Earth's extended magnetotail, the long trailing structure on the night side of the magnetosphere, still provides a measurable reduction in cosmic ray intensity. This cavity does not extend all the way to the Moon at all times. It fluctuates with solar activity and with the orientation of Earth's magnetotail relative to the Sun. But it suggests that the transition from protected to unprotected is not a clean break. It is a messy, variable, partially shielded zone where the magnetic field still has a fading grip on the particle environment. The grip is fading. It is not gone yet in cislunar space, but it is weakening with every kilometer outward. And once you pass beyond the magnetotail entirely, it is gone for good. The Apollo astronauts were the first humans to experience this transition. Between 1969 and 1972, 24 people traveled beyond low Earth orbit to the Moon. They passed through the Van Allen belts on the way out and again on the way back, spending a limited time in the most intense radiation zones. NASA carefully planned the trajectories to minimize belt exposure, and the transits were fast enough that cumulative doses remained within acceptable limits. But once the astronauts cleared the belts and entered the deep space environment between Earth and the Moon, they encountered something no human being had experienced before: unshielded cosmic radiation. The effect was subtle but unmistakable. Multiple Apollo crew members reported seeing brief flashes of light even with their eyes closed, especially during dark periods when they were trying to sleep. These were not malfunctions of the spacecraft lighting. They were not hallucinations caused by fatigue. They were caused by individual cosmic ray particles, heavy ions moving at relativistic speeds, passing through the eyeball and striking the retina or the optic nerve directly. Each impact triggered a tiny burst of perceived light, a miniature flash lasting a fraction of a second. The phenomenon was documented across several missions. Astronauts on Apollo 11 reported it. Crew members on Apollo 14 described it in more detail. A dedicated experiment on Apollo 16 used a device called the Apollo Light Flash Moving Emulsion Detector to correlate the flashes with actual particle impacts. The results confirmed that cosmic rays were responsible. Every flash was a high-energy particle punching through the astronaut's skull and interacting with biological tissue. Think about what that means. Each flash of light was a single atomic nucleus, often carbon, oxygen, or iron, stripped of its electrons, moving at close to the speed of light, carrying enough energy to damage DNA at the cellular level. The astronauts experienced these flashes roughly once or twice per minute during quiet solar conditions. Each one was harmless on its own, but each one was also a reminder that the human body was never designed for this environment. Evolution built us for the bottom of an atmosphere 10,000 kilometers thick, protected by a magnetic field that deflects the vast majority of these particles before they ever reach the ground. Remove those protections, and the particles come straight through, not through the walls of the spacecraft, through the walls of the spacecraft, and through the walls of your cells. The radiation measurements from the Apollo era confirmed what physicists had predicted. Outside the magnetosphere, the primary radiation threat comes from two sources. The first is solar energetic particles, bursts of protons and heavier ions accelerated to enormous speeds by solar flares and coronal mass ejections. These events are sporadic and unpredictable, but when they occur, they can deliver lethal doses of radiation within hours to anyone caught without adequate shielding. The second source is galactic cosmic rays, a constant background of high-energy particles that originate not from the sun, but from supernova explosions and other violent events scattered throughout the galaxy. Galactic cosmic rays are less intense than a major solar particle event, but they never stop. They arrive from every direction at all times, and they include the heaviest and most energetic particles in nature. Some carry energies that make even the most powerful particle accelerators on Earth look modest. Apollo was lucky. None of the missions coincided with a major solar particle event. Had a large flare occurred during a translunar coast, or while astronauts were on the lunar surface, the consequences could have been severe. NASA scientists calculated afterward that a solar event comparable to the August 1972 flare, which happened between the Apollo 16 and Apollo 17 missions, could have delivered a potentially lethal radiation dose to astronauts in deep space. The timing was a matter of months. A different launch schedule could have put a crew in the path of that storm with nothing between them and the incoming protons except a thin shell of aluminum and their own skin. This is not ancient history. It is current engineering reality. Every crewed mission planned for deep space, including NASA's Artemis program to return humans to the moon, must contend with these same radiation risks. The Artemis II mission, which carried astronauts around the moon, involved careful radiation monitoring throughout the flight. Planning for longer lunar surface stays and eventual Mars missions requires even deeper understanding of the radiation environment beyond Earth's magnetosphere. The challenge is not theoretical. It is practical, measurable, and currently unsolved in any complete sense. You can reduce exposure. You can build storm shelters within spacecraft. You can time missions to avoid the peak of the solar cycle. But you cannot recreate Earth's magnetosphere around a spacecraft. That protection exists in exactly one place in the solar system, and it is the place you are leaving behind. Radiation is not the only thing that changes when you leave low Earth orbit. Something else shifts, something harder to quantify, but equally important. It is the relationship between you and home. On the International Space Station, Earth fills nearly half the sky. It is enormous, luminous, and overwhelmingly present. You can see continents, weather systems, city lights at night. You can identify the country you grew up in. Communication with the ground takes a fraction of a second. A radio signal from the station reaches mission control in Houston almost instantaneously. If something goes wrong, if a micrometeorite punctures the hull, if a system fails, if an astronaut has a medical emergency, help is close. Not immediate, but close. A crew could theoretically evacuate the station and return to Earth's surface within hours using the docked Soyuz or Crew Dragon capsules. The station is remote, but it is not isolated. It is tethered to Earth by communication, by proximity, by the constant visual presence of the planet that built it. Move to the moon, and that tether stretches thin. Communication delay to the lunar surface is approximately 1.3 seconds each way. That sounds trivial, and for most purposes, it is. You can hold a conversation with a slight awkward pause, like a bad video call. But it is enough to make real-time control of complex systems difficult. More importantly, the visual relationship with Earth changes dramatically. From the surface of the moon, Earth appears as a small disk in the sky, roughly 4 times the apparent diameter of the moon as seen from Earth. Bright and beautiful, but clearly distant. You can cover it with your thumb held at arm's length. It is no longer the overwhelming presence that dominates the view from the station. It is an object, a destination you came from, a place that is there, not right here. And rescue becomes a different calculation entirely. A crew on the lunar surface experiencing a critical emergency cannot simply climb into a capsule and be home in hours. The return journey from the moon takes approximately 3 days. 3 days of coasting through cislunar space, exposed to whatever radiation environment exists at that moment, relying entirely on the spacecraft systems to function correctly. If the main engine fails, if the heat shield is compromised, if the life support system develops a critical fault during that coast, there is no backup. There is no second vehicle waiting to pick you up. There is no gas station, no hospital, no safe harbor between the moon and the atmosphere. You are 3 days from the only place in the universe that can keep you alive without a machine. Now imagine what those 3 days feel like from the inside. The capsule is small, not airplane cabin small, smaller. The habitable volume of an Apollo command module was roughly 6 cubic meters, and modern deep space capsules are not dramatically larger. 3 people share a space about the size of a large closet, surrounded by instrument panels, storage lockers, and the constant hum of fans circulating the air that keeps carbon dioxide from settling around their faces. There is no room to stretch your legs. There is no room to walk. There is barely room to turn around without brushing a switch or bumping a crewmate's shoulder. You eat pre-packaged meals that taste like their packaging. You sleep in shifts, strapped loosely into position so you do not drift into the control panel while unconscious. The toilet is a device you would not want described to you in detail, and it is less than an arm's length from where someone else is eating. Outside the window, the view depends on which direction you are facing. On the sunward side, Light pours in so intensely that you must shade the glass to avoid overheating the interior. On the opposite side, the blackness is absolute, not the darkness of a room with the lights off, where your eyes eventually adjust and shapes emerge. The blackness of cislunar space on the anti-sun side is a void so complete that your visual cortex has nothing to process. No gradient, no depth, no hint of distance. Just black, pressing against the glass like a solid surface. Your brain interprets it as a wall, because a wall is the closest thing it has ever experienced to a visual field with zero input. But it is not a wall. It is 238,000 miles of nothing between you and the atmosphere. During those 3 days, the cosmic ray flashes continue. They come while you are eating. They come while you are running system checks. They come while you are trying to sleep. Each one is a brief streak or a tiny point of blue-white light behind your eyelids. And each one is a high-energy particle that just passed through the capsule wall and through your skull. You cannot stop them. You cannot shield against the most energetic ones. You can only know that they are happening. That each flash represents a particle impact on biological tissue, and that the cumulative dose is climbing with every hour you spend outside the magnetosphere. You are not in immediate danger. The dose rate during a quiet solar period is manageable for a 3-day transit. But if the sun erupts, if a coronal mass ejection launches a wall of protons in your direction while you are coasting through unshielded space between the moon and the Van Allen belts, the calculus changes in minutes. There is nowhere to hide. The capsule offers minimal shielding. The best you could do is orient the spacecraft so the thickest part of the heat shield faces the incoming storm and huddle behind whatever mass you can place between yourself and the radiation. Storage containers, water tanks, equipment bags, anything that puts material between the protons and your body, it would help. It would not be enough for a large event. And you would know that, sitting in your closet-sized capsule, watching the radiation monitor climb, 3 days from the only atmosphere that could save you. And then, slowly, Earth begins to grow. Through the window on the approach side, the planet appears first as a blue star, then as a small disk, then as something recognizable. Continents take shape. Cloud patterns become visible. The familiar colors emerge. The turquoise of shallow oceans, the amber of deserts, the white spiral of a cyclone. It gets larger with every hour, and as it grows, something happens that astronauts have described, but that no measurement can capture. Relief. Not relief in the casual sense of a problem solved. Relief in the physiological sense. A release of tension so deep that it registers in the chest before the brain can name it. The planet is there. Home is there. The atmosphere is there, waiting to catch you, waiting to slow you from 7 miles per second to 0, waiting to wrap you in air and gravity and warmth and the entire infrastructure of a civilization that exists nowhere else. Every system that vanished when you left, the magnetic field, the radiation shielding, the breathable air, the instant communication, the rescue capability, all of it is still there, still working, still waiting. You just have to survive the next 72 hours to reach it. That relief, that visceral, aching pull toward home, is something that no astronaut who has traveled beyond low Earth orbit has failed to report. It is not sentimentality. It is biology recognizing the only environment in the known universe where it can survive unaided. And it is the last time in this journey outward that you will feel it this strongly. Because beyond the moon, Earth does not grow larger as you approach. It shrinks. And the farther you go, the smaller it gets, until the relief becomes a memory, and the memory becomes an ache, and the ache becomes a silence that the universe does not answer. The moon is close. By the standards of the solar system, it is absurdly close. Light takes barely over a second to reach it. Spacecraft can get there in 3 days. The Apollo program did it with 1960s technology, with computers less powerful than a modern pocket calculator. The moon is close enough that we can see it with the naked eye on any clear night, close enough that its gravity raises tides in our oceans, close enough that it feels like a neighborhood destination rather than a foreign world. And yet, even at this trivial cosmic distance, the protections have already started to fall away. The magnetosphere is gone. The atmosphere was gone the moment you left the launch pad. Radiation is higher. Communication has a delay. Rescue takes days instead of hours. Resupply depends on launches that take months to prepare. Every single one of these changes is manageable at lunar distance. Astronauts have survived them before and will survive them again. But they are not nothing. They are the first layer being peeled away. The first set of invisible systems that kept you safe without you ever noticing, now absent, replaced by machines and planning and a narrow margin of error that did not exist when you were standing on the ground beneath 60,000 miles of magnetic shielding and 60 miles of atmosphere. This is what most people miss about space travel. They imagine the danger is dramatic. An explosion on the launch pad, a catastrophic hull breach, a collision with an asteroid. Those risks exist, but they are not what makes deeper space more horrifying. What makes it horrifying is the quiet subtraction. Each threshold you cross removes something you relied on, something so fundamental that you never thought of it as a protection at all. The atmosphere was protection. You did not think about it until it was gone. The magnetic field was protection. You did not think about it until the cosmic rays started flashing in your eyes. Rapid communication was protection. You did not think about it until the delay stretched long enough to make help impractical. The ability to come home quickly was protection. You did not think about it until the return trip became measured in days rather than hours. Every one of these losses is permanent once you move beyond the threshold. There is no way to get the magnetosphere back once you leave it. There is no way to reduce the communication delay except by moving closer to Earth. There is no way to shorten the rescue timeline except by not going as far. Every protection that falls away stays away. And the deeper you go, the more of them you lose. But the moon is the last place where Earth can still reach you in any meaningful sense. The delay is short. The distance is crossable in days. The radiation is elevated, but survivable. The sun is still bright, still warm, still clearly the dominant source of energy in your sky. Everything beyond this point changes that equation. Not slightly, fundamentally. Because once you leave the Earth-Moon system and head outward into interplanetary space, you cross into a region where distances become so vast that communication stops being a conversation. Sunlight stops being a reliable power source. Rescue stops being a possibility. And the sun itself begins to lose its grip on the space around you. The first shield has already fallen. The next ones fall harder, and they do not come back. The moment you leave the Earth-Moon system and aim outward, something happens that no photograph can fully communicate. Earth shrinks. Not gradually in the way a city shrinks in a rearview mirror, but relentlessly, collapsing from a bright disk to a brilliant point to just another dot in a field of stars. The moon, which seemed like a destination when you were standing on it, becomes an afterthought. A tiny companion circling a tiny point of light that used to be everything you knew. And the sun, which dominated your sky in low Earth orbit and still blazed overhead on the lunar surface, begins a long, slow retreat. It does not go out. It does not vanish. It simply becomes less bright, less warm, less powerful, less able to protect you. And with every 1,000,000 kilometers you travel outward, the systems that depended on it begin to fail. Mars is the first real test of what interplanetary distance does to the human relationship with home. At its closest approach, Mars sits roughly 34 million miles from Earth. At its farthest, when the two planets are on opposite sides of the Sun, the distance stretches to over 250 million miles. The average distance is approximately 140 million miles. These are numbers that mean almost nothing to the human brain. So let me translate them into the only currency that matters for survival: time. A radio signal travels at the speed of light. From Earth to Mars, depending on orbital positions, that signal takes between 3 and 22 minutes to arrive. One way, not round trip, one way. If you are an astronaut standing on the Martian surface and you radio mission control to say you have a problem, you will wait a minimum of 6 minutes for a response. 6 minutes of silence after reporting an emergency. During solar conjunction, when the Sun sits directly between Earth and Mars, communication is blocked entirely for approximately 13 days. No signals in, no signals out. Total blackout. Most people hear those numbers and think they sound manageable. 3 minutes is nothing. You wait longer than that for a traffic light. But consider what 3 to 22 minutes of delay actually means in practice. It means you cannot have a conversation. Communication becomes a series of monologues separated by gaps long enough to make the exchange feel like sending letters rather than speaking. You transmit a message. You wait. You receive a reply that refers to what you said many minutes ago, long after the situation may have changed. You respond to that reply, and the cycle continues. Always lagging, always outdated, always referring to a version of reality that no longer exists by the time the words arrive. NASA already understands this problem because they have been living with it for decades through their robotic Mars missions. The Perseverance rover does not wait for instructions from Earth before navigating around a rock. It cannot. If Perseverance encountered a hazard and radioed for guidance, the signal would take somewhere around 12 minutes to reach the Jet Propulsion Laboratory. The engineers would need time to analyze the situation and formulate a response, and their instructions would take another 12 minutes to travel back to Mars. Nearly half an hour would pass between the rover encountering a problem and receiving instructions about what to do. In that time, the rover could have driven off a cliff. So instead, Perseverance uses an autonomous navigation system called AutoNav that processes terrain images on board and makes its own driving decisions in real time. The rover thinks for itself because Earth is too far away to think for it. Now, put a human crew in that same situation. Not a rover that can be replaced for a few $1 billion, living, breathing people with families back home. An astronaut on Mars suffers a medical emergency. A suit breach during a spacewalk. A fall that fractures a femur. A sudden cardiac event. The crew radios Earth. The message crawls across interplanetary space at the speed of light. 12 minutes later, the flight surgeon hears the report. The surgeon consults with specialists, reviews the data, and transmits instructions back. Another 12 minutes. By the time the crew receives medical guidance, nearly half an hour has passed since the emergency began. In trauma medicine, half an hour is not a delay. It is a lifetime. Outcomes in cardiac arrest, in severe hemorrhage, in tension pneumothorax, are often decided in the first 5 to 10 minutes. The crew on Mars will have to handle those first critical minutes entirely on their own, with whatever training they received before launch and whatever medical equipment they carried with them. Earth cannot help. Not because Earth does not want to help, but because physics will not let it. This is a fundamentally different kind of danger from anything that exists in low Earth orbit or even at the Moon. On the International Space Station, an emergency triggers an immediate response. Voice communication with the ground is essentially instantaneous. Mission control can talk a crew through a procedure in real time, monitor telemetry as it happens, and coordinate a response that involves hundreds of people working together across multiple facilities. At the Moon, the 1.3-second delay introduces a slight awkwardness, but does not fundamentally break this dynamic. At Mars, the dynamic is broken. The crew is alone in every way that matters during a crisis. Not because they are abandoned, but because the universe is too large for help to arrive in time. But the communication delay is not the only thing that changes at Mars. Something subtler happens. Something that engineers can quantify, but that astronauts will feel in their bones. Earth disappears. Not from the radio, not from the navigation charts, from the sky. In low Earth orbit, Earth fills your field of view. At the Moon, it is a bright disk you can cover with your thumb. At Mars, Earth is a pale blue point of light in the evening or morning sky. No brighter than a moderately bright star. If no one pointed it out to you, you might not find it at all among the background stars. Every astronaut who has ever flown in space has described the psychological power of seeing Earth. The overview effect, the emotional shift that comes from witnessing the whole planet at once, has been reported by nearly every crew member who has experienced it. That effect depends on proximity. It depends on Earth being visible as a world rather than a point. At Mars, the overview effect reverses. Earth is no longer a world you can see. It is a dot you have to search for. And that dot is everything. Every person you have ever known, every place you have ever lived, every hospital and factory and grocery store and fire station, all of it condensed into a flicker of reflected sunlight that your eye can barely distinguish from the stars around it. The psychological literature on long-duration isolation missions consistently identifies one factor above all others that determines crew morale: the perceived connection to home. Submarine crews maintain it through scheduled radio contact. Antarctic winter-over teams maintain it through satellite links that allow near real-time communication. Both of those environments offer something Mars cannot: the knowledge that home is reachable. A submarine can surface. An Antarctic base can be evacuated by air in an emergency. Mars cannot be left on short notice. The crew commits knowing that the return window is fixed, that the journey home will take months, and that during the entire stay, every interaction with Earth will carry a delay long enough to make it feel like talking to a memory rather than a person. You are speaking to someone who heard your last sentence many minutes ago. They are responding to the version of you that existed before your current sentence began. The conversation is always behind. The present moment on Mars is a place that only the people on Mars inhabit. Earth lives in the past tense. This perceptual and psychological shift is the hidden threshold of interplanetary space. The physical hazards, radiation, dust, thermal stress, are engineering problems with engineering solutions. The disappearance of Earth as a visible, reachable, present-tense home is something else entirely. It is the first moment in the journey where the loss is not just physical, but existential. You are no longer on a mission from Earth. You are on a mission from a dot. And Mars is close. Mars is the nearest planet that humans have serious plans to visit. It sits at roughly 1.5 astronomical units from the Sun. 1 astronomical unit is the average distance from Earth to the Sun, about 93 million miles. At 1.5 astronomical units, Mars still receives a substantial amount of sunlight. The solar intensity at Mars averages approximately 588 watts per square meter, compared to roughly 1,361 watts per square meter at Earth. That is about 43% of Earth-level sunlight, enough to power solar panels, though they need to be larger than Earth-based equivalents to produce the same output. Enough to provide warmth, although surface temperatures on Mars average around -60 degrees Fahrenheit and can plunge to -190 near the poles. The sun at Mars is dimmer, but it is still recognizably the sun. Move outward, and the sun weakens faster than intuition suggests. This is because sunlight does not diminish at a steady rate as you travel away from it. It follows the inverse square law, one of the simplest and most unforgiving equations in physics. Double your distance from the sun, and the light intensity drops not by half, but to 1/4. Triple the distance, and it falls to 1/9. The relationship is exponential in its cruelty. Every additional step outward costs you disproportionately more light, more warmth, more energy. The asteroid belt sits between roughly 2 and 3.3 astronomical units from the sun. At 2.8 astronomical units, the approximate midpoint, sunlight drops to about 1/8 of what reaches Earth. Spacecraft operating in the asteroid belt can still use solar panels, but they need to be significantly larger. NASA's Psyche mission, which visited an asteroid in this region, carried solar panels with an area of about 75 square meters to generate adequate power. Compare that to a spacecraft in Earth orbit that might need only a fraction of that area for the same electrical output. The panels are not just larger, they are heavier, more complex, and more vulnerable to micrometeoroid damage across all that additional surface area. Every square meter of solar panel is a square meter that could be punctured by a grain of dust traveling at tens of kilometers per second. But the real transformation happens at Jupiter. Jupiter orbits at approximately 5.2 astronomical units from the Sun. Apply the inverse square law. 1 divided by 5.2 squared gives you roughly 0.037. At Jupiter, sunlight is approximately 3.7% of what reaches Earth. If sunshine on a clear summer day feels like standing next to a bonfire, the sunlight at Jupiter feels like the warmth of a single candle burning in a stadium. You could hold your hand out and feel almost nothing. Your eyes would still see the sun as a bright point in the sky, but its disk would appear noticeably smaller than what you are used to. From Jupiter, the sun is still the brightest object in the sky by far, but it no longer feels like a furnace. It feels like a lamp in an enormous cold room. The thermal consequences are severe and extend far beyond simple discomfort. Spacecraft operating at Jupiter must manage extreme cold on their shaded surfaces, while potentially dealing with heating on their sun-facing sides, creating thermal gradients that stress materials and complicate engineering. The European Space Agency's Jupiter Icy Moons Explorer and NASA's Europa Clipper mission both carry sophisticated thermal management systems specifically because the solar environment at Jupiter is so hostile in its coldness. What most people do not understand about spacecraft thermal management is that cold is not just cold, it is a mechanical force. Materials contract at different rates as temperatures drop. A metal bracket bonded to a composite panel will shrink differently from the panel itself, and over repeated thermal cycles, that mismatch generates stress. Seals designed to remain flexible at room temperature can stiffen and crack at -150 degrees Fahrenheit. Lubricants in moving parts thicken or freeze entirely. Electrical connectors that fit precisely at Earth temperatures develop microscopic gaps as the metal around them contracts, and those gaps can cause intermittent faults that are almost impossible to diagnose remotely. The cold of deep space does not simply chill a spacecraft. It attacks every joint, every seal, every interface between dissimilar materials, every moving part that depends on precise tolerances to function. Engineers spend years designing thermal control systems to manage these effects, layering insulation blankets, positioning electrical heaters at critical points, routing heat from electronics that generate waste warmth to components that need it. In low Earth orbit, this thermal management is straightforward because the sun provides abundant energy. At Jupiter, the sun provides almost nothing, And the only heat available is what the spacecraft generates internally from its own power source. Every watt spent on a heater is a watt that cannot power an instrument, a communication transmitter, or a reaction wheel. Staying warm competes directly with every other function the spacecraft must perform. And then there is the power problem. At 3.7% of Earth-level sunlight, solar panels become enormously challenging. The Juno spacecraft, which has been orbiting Jupiter since 2016, became the most distant solar-powered spacecraft at the time. Its 3 solar arrays cover a combined area of over 60 square meters, and at Jupiter, they generate roughly 500 watts of electricity. 500 watts, enough to power roughly 5 household light bulbs. The entire spacecraft, one of the most sophisticated robotic explorers ever built, operates on the electrical output of a small portable generator. Juno made it work through extreme efficiency in every system, but the engineering margin is razor thin. There is no surplus power. There is no reserve. Every watt is allocated. Every circuit is optimized. A single system failure could cascade into a power shortfall that compromises the entire mission. Earlier missions to Jupiter did not even attempt solar power. Voyager 1 and Voyager 2, which flew past Jupiter in 1979, used radioisotope thermoelectric generators, devices that convert the heat from decaying plutonium-238 into electricity. These generators do not depend on sunlight. They produce power from radioactive decay, which continues regardless of distance from the sun. This made them essential for missions to the outer solar system, where solar panels were not viable with the technology available at the time. The Galileo orbiter, which studied Jupiter from 1995 to 2003, also used radioisotope thermoelectric generators. So did the Cassini mission to Saturn and the New Horizons mission to Pluto and beyond. The reliance on radioisotope power at Jupiter and beyond reveals something important about the nature of the threshold you are crossing. Inside roughly 3 astronomical units, the sun provides enough energy that you can harvest it directly. You are still within the sun's energetic reach. Beyond that distance, the sun's output becomes too dilute for practical solar power with current or near-future technology. You must bring your own energy source. You must carry fuel that does not depend on the star you are leaving behind. This is not just an engineering inconvenience. It is a conceptual shift. You are no longer living off the sun's energy. You are living off something you packed in a box before you left home. Now, layer the communication problem on top of the power problem. At Jupiter's distance, one-way light time ranges from roughly 33 to 54 minutes, depending on orbital positions. A round-trip exchange with Earth takes over an hour at minimum. If a spacecraft at Jupiter encounters a problem, mission control will not learn about it for half an hour or more, and any instructions they send will take another half hour to arrive. For robotic missions, this is challenging but manageable. Engineers program autonomous fault protection routines that allow the spacecraft to save itself, shutting down non-essential systems and orienting to maintain communication with Earth. For a hypothetical crewed mission, the implications are staggering. An hour-long communication delay means the crew is functionally independent. Earth-based expertise becomes advisory, not operational. Every real-time decision, every diagnosis, every repair, every judgment call during an emergency belongs to the people on site, with no possibility of real-time consultation. And then there is Jupiter's own contribution to the hazard landscape, one that shatters the assumption that danger simply increases smoothly with distance from Earth. Jupiter possesses the most powerful magnetic field of any planet in the solar system, roughly 20,000 times stronger than Earth's. This magnetic field traps charged particles from the solar wind and from volcanic material ejected by its moon Io. creating radiation belts that make Earth's Van Allen belts look gentle by comparison. The radiation environment near Jupiter is so intense that it can damage spacecraft electronics within hours. The Juno spacecraft was designed with a titanium radiation vault weighing about 440 pounds, specifically to protect its most sensitive instruments from Jovian radiation. Even with that vault, Juno follows a highly elliptical orbit that minimizes time spent in the most dangerous radiation zones near the planet. This matters because it demonstrates a principle that the rest of this journey will reinforce. The hazards of deep space do not simply increase in a straight line as you move farther from Earth. They change character. In low Earth orbit, the primary concern is micrometeoroid impact and the manageable radiation environment inside the magnetosphere. At the Moon, the concern shifts to unshielded cosmic radiation and the loss of rapid rescue. At Mars, it becomes communication delay and isolation. At Jupiter, you encounter a localized radiation nightmare that is worse than anything between Earth and Mars. Not because Jupiter is farther away, but because Jupiter is Jupiter. It has its own magnetic field, its own trapped particle population, its own lethal radiation environment that exists independently of distance from the Sun. Moving past Jupiter, the radiation threat from Jupiter itself drops off quickly. But new threats emerge. The sunlight continues to weaken. The cold deepens. The communication delay stretches further. And the possibility of repair or resupply from Earth transitions from difficult to absurd. Consider what repair means at these distances. On the International Space Station, a critical component fails. A replacement can be launched from Earth and delivered within weeks, sometimes faster. The crew can perform a spacewalk to install it. They have tools, spare parts, and ground support walking them through every step in real time. At Mars, a critical failure means waiting for the next launch window, which opens approximately every 26 months when Earth and Mars align favorably. If something breaks 6 months after the last supply ship arrived, the crew may have to wait 2 years for a replacement, assuming one can be launched at all. They must carry extensive spare parts and possess the skills to fabricate replacements from available materials. At Jupiter, no crewed resupply mission has ever been attempted or even seriously planned. The transit time from Earth to Jupiter using conventional propulsion is roughly 5 to 7 years. 5 years. If a critical life support component fails on a crewed vessel at Jupiter, Earth cannot send help in time, not in any practical sense. The crew must fix it themselves using whatever they brought, or they die. There is no middle option. There is no partial rescue. There is no limping home on backup systems while a supply ship races to meet you. The distances are too great. The transit times too long. The energy requirements too enormous. You are on your own in a way that no human being has ever been on their own before, surrounded by equipment that must work perfectly because the nearest replacement is 5 years and several billion kilometers away. What makes this escalation so treacherous is that it does not announce itself as a cliff. It presents itself as a slope. At the Moon, if a water recycling unit fails, you can survive on stored water for the 3-day journey home. At Mars, if the same unit fails, you activate the backup and begin fabricating replacement filters from materials you packed specifically for this scenario. You have trained for it. You have spares. You are stressed, but you are managing. At Jupiter, the same failure looks entirely different. There may be no backup unit because the mass budget did not allow for 2 of everything. The spare filters you packed for Mars have already been used. The materials you might fabricate a workaround from are limited to whatever you can cannibalize from systems you no longer need. And you cannot call Earth to brainstorm solutions in real time because the round-trip delay exceeds an hour. You are alone with the problem. alone with your training, alone with whatever tools fit inside the spacecraft when it launched years ago. The slope between Mars-level self-sufficiency and Jupiter-level self-sufficiency is the slope between difficulty and desperation. At Mars, a mechanical failure is a serious problem. At Jupiter, the same failure can become a death sentence, not because the failure is worse, but because the support structure around you has thinned to almost nothing. And this slope continues tilting. Every astronomical unit beyond Jupiter increases the transit time, the communication delay, the thermal stress, and the total mass of consumables needed to survive the journey. By the time you reach Saturn, a crewed resupply mission from Earth would take roughly 7 to 9 years. Any part that breaks must be fixable with tools and materials already on board. Any illness must be treatable with the pharmacy already stocked. Any injury must be surgically manageable by the crew themselves. The spacecraft becomes a closed world, not metaphorically, but literally. Nothing comes in, nothing goes out, except radio signals that take over an hour to reach anyone who might understand them. The crew is not exploring space. The crew is surviving inside a machine, and the machine is the only thing between them and an environment that will kill them in seconds if it finds a way through. Interplanetary dust adds another quiet hazard that most people never consider. The space between the planets is not empty. It contains a diffuse cloud of particles, remnants of asteroid collisions, cometary debris, material that has been drifting through the inner solar system for millions of years. Most of these particles are extraordinarily small, grains smaller than a grain of sand, some no larger than a few micrometers across. But at the relative velocities involved in interplanetary travel, even microscopic particles carry significant kinetic energy. A fleck of paint traveling at orbital velocities once cracked a window on the space shuttle. A dust grain, 1/10 of a millimeter across, striking a spacecraft at 12 miles per second, can excavate a crater several millimeters wide in aluminum. Over long-duration missions, the cumulative effect of thousands of microscopic impacts gradually degrades surfaces, pits optical elements, and erodes thermal protection coatings. No single impact is catastrophic. The accumulation is the danger. Beyond the asteroid belt, the interplanetary dust density decreases somewhat, but it does not vanish. And as you approach Jupiter, a new source of particulate hazard appears. Jupiter's enormous gravity captures and concentrates debris in its vicinity. Its ring system, far less spectacular than Saturn's, consists of fine dust particles that present a collision risk to spacecraft passing through the equatorial plane. The Galileo mission detected impacts from ring particles during its orbital insertion. These particles are small, but they are fast relative to an orbiting spacecraft, and they are unavoidable if your trajectory passes through the ring plane. Every one of these factors, radiation, power, thermal management, communication delay, repair limitations, and dust, represents a system of protection or capability that weakens or disappears as you move outward from Earth. None of them, individually, would stop a determined civilization from exploring interplanetary space. Together, they define the character of that space. It is not simply far. It is far in ways that remove specific capabilities and specific safeties, layer by layer, system by system, until the spacecraft and its crew are operating in an environment that Earth-based intuition cannot adequately model. You think you understand what it means to be far from home until you realize that far from home means far from hospitals, far from factories, far from communication, far from warmth, far from light, and far from every supply chain that modern civilization depends on. But Jupiter is still inside the sun's domain. Every photon that reaches it, every particle of solar wind that streams past its magnetosphere, every faint ripple of solar magnetic field extending this far, all of it is proof that the sun still has influence here. The solar wind is weaker at Jupiter, but it is present. Sunlight is dim, but it is real. Beyond the outer planets, that influence begins to falter. The solar wind thins. The sunlight fades toward irrelevance. The magnetic field of the sun becomes so attenuated that it can barely be distinguished from the background noise of the galaxy. And somewhere out there, at a distance that varies with solar activity and the pressure of the interstellar medium pushing inward, the sun's influence ends entirely. That boundary has a name. Reaching it is the next threshold, and crossing it means leaving the only star that has ever kept you alive. Beyond Jupiter, the solar system becomes a place that human senses were never calibrated to understand. Saturn orbits at 9.5 astronomical units from the Sun. Uranus drifts at just over 19. Neptune circles at 30. These distances are so large that expressing them in everyday units becomes almost an act of absurdity. Neptune's average distance from the Sun is approximately 2.8 billion miles. If you drove a car at highway speed toward Neptune without stopping, you would arrive in roughly 5,000 years. The outer solar system does not merely stretch beyond the inner planets. It dwarfs them. Everything that feels vast about the distance between Earth and Mars, the communication delays, the weakened sunlight, the isolation, becomes a faint echo of what waits beyond Saturn's rings. The sunlight continues to obey the inverse square law, and by now, that law has become punishing. At Saturn, sunlight drops to about 1% of Earth-level intensity. 1%. Think about what that actually looks like. On Earth, a cloudless afternoon delivers enough solar energy per square meter to blind you if you stare at the source. 1% of that intensity is not dim in the way a cloudy day is dim. It is dim in the way a room lit by a single nightlight is dim. The landscape would be visible. You could see shapes, surfaces, the curve of a ring system catching what little light arrives. But the quality of that light would feel profoundly wrong to any human eye adapted to terrestrial conditions. Shadows would be softer, colors muted, and the emotional register of the environment would shift from daylight to perpetual dusk. There would be no warmth on your face, no sense of the sun bearing down, just a faint cold glow arriving from a source that your brain still identifies as the sun, but that your body no longer recognizes as one. NASA's Cassini spacecraft, which orbited Saturn for 13 years, relied on radioisotope thermoelectric generators for power because solar panels at that distance were not feasible with the technology of its era. When Cassini released the Huygens probe to descend through the atmosphere of Saturn's moon Titan in January 2005, the probe carried batteries rather than solar panels. At 9.5 astronomical units from the Sun, harvesting sunlight is an exercise in diminishing returns that borders on futility. When Huygens broke through Titan's thick orange haze and reached the surface, it landed in a world illuminated by roughly 1% of Earth's sunlight, filtered further through a nitrogen-rich atmosphere roughly 5 times denser than Earth's at the surface. The images it returned showed a landscape of rounded ice pebbles and what appeared to be a dried riverbed carved by liquid methane. The lighting in those photographs looks like an overcast winter afternoon in the far north. Except the color temperature is wrong, shifted toward a sickly amber by the atmospheric haze. To a human standing there, Titan's surface would feel like being outdoors on Earth during a deep twilight. The kind of light where you can read a page if you hold it close, but where distances become uncertain and depth perception falters. And that is with an atmosphere scattering and redistributing the light. In open space at Saturn's distance, without an atmosphere to diffuse the sunlight, the sun would appear as a small, sharp, blindingly bright point surrounded by absolute blackness. bright enough to damage your eyes if you looked at it directly, but contributing so little energy to your surroundings that everything not in its direct line of sight would register as functionally dark. The paradox of the outer solar system is that the sun remains dangerous to look at long after it has stopped being useful for anything else. At Uranus, 19 astronomical units out, sunlight drops to roughly 1/360th of Earth-level intensity. The sun is still visible as the brightest point in the sky, but it has lost the quality of being a sun in any experiential sense. It does not warm you. It does not illuminate the landscape the way sunlight on Earth does. It is a bright star, the brightest star, yes, but a star, not a furnace. And with the sunlight goes the last trace of thermal generosity from the sun. At Uranus, the equilibrium temperature for a surface in direct sunlight drops to around -353 degrees Fahrenheit. At these temperatures, most common gases would exist as liquids or solids. Methane freezes. Ammonia freezes. Carbon dioxide has been a solid since well before Jupiter's orbit. The only substances that remain gaseous at these temperatures are hydrogen, helium, and neon. The cold at Uranus is not just extreme. It is a different category of cold. A regime where the thermal energy available from the sun is so negligible that the dominant thermal influence on a spacecraft is its own internal heat generation and the faint glow of the cosmic microwave background. A spacecraft at Uranus that lost all internal power would cool over days and weeks toward a temperature just a few degrees above absolute zero. Every fluid in its systems would solidify. Every seal would contract. Every wire would become brittle. The spacecraft would not explode or break apart. It would simply freeze, slowly and completely, into a monument to the absence of the sun's warmth. No spacecraft has orbited Uranus. Voyager 2 flew past it in January 1986, snapping images during a brief encounter window and then continuing onward. That flyby remains our only close visit. Commands for the flyby had to be uploaded to the spacecraft well in advance because the one-way light time to Uranus was approximately 2 hours and 45 minutes. Real-time control was impossible. Every maneuver, every camera pointing sequence, every instrument activation had been planned, tested, and loaded into the spacecraft's memory long before the encounter began. Voyager 2 executed the flyby on its own, following instructions composed hours earlier by engineers who could only watch the results arrive long after the events had already occurred. Neptune is where the transformation becomes undeniable. At 30 astronomical units, sunlight is approximately 1/900th of what reaches Earth. The sun, seen from Neptune's distance, is a brilliant point of light that you could almost mistake for a particularly bright planet if you did not know better. It still outshines everything else in the sky. It is still unmistakably the center of the solar system if you understand orbital mechanics. But it has lost the visceral authority that the sun carries when you stand on Earth and feel its heat on your face. From Neptune, the sun is a memory of warmth rather than warmth itself. Voyager 2 reached Neptune in August 1989, and that encounter remains one of the great achievements of robotic space exploration. The spacecraft flew within 3,000 miles of Neptune's cloud tops, discovered 6 new moons, confirmed the existence of the planet's ring arcs, and captured images of the Great Dark Spot, a storm system the size of Earth. It then swept past Triton, Neptune's largest moon, revealing a world of nitrogen geysers and a surface temperature of -391 degrees Fahrenheit, one of the coldest measured surfaces in the solar system. The one-way light time during the encounter was approximately 4 hours and 6 minutes. When engineers at the Jet Propulsion Laboratory received confirmation that the flyby had succeeded, the event itself was already more than 4 hours in the past. They were celebrating something that had already happened. watching a recording delivered at the speed of light from a distance so great that the word far stops being adequate. 4 hours of communication delay changes the nature of the relationship between a spacecraft and its operators. In low Earth orbit, communication is a conversation. At the Moon, it is a conversation with an awkward pause. At Mars, it is an exchange of messages. At Jupiter, it is correspondence. At Neptune, it is something closer to whispering across a canyon so wide that you must shout your message, wait half a day for the echo, and hope the other side understood. The round-trip time exceeds 8 hours. If Voyager 2 had encountered a problem during its Neptune flyby, the engineers would not have learned about it for 4 hours. Any corrective command they sent would not have arrived for another 4 hours. 8 hours of helplessness, during which the spacecraft would either solve its own problems or fail. At these distances, the spacecraft is not an extension of human will operated from a control room. It is an autonomous agent carrying a set of instructions written by people who could only guess at what conditions it would encounter. Beyond Neptune lies the Kuiper Belt, a vast ring of icy bodies extending from roughly 30 to 50 astronomical units. This is where Pluto orbits, along with its moons, and where thousands of other frozen worlds drift in near total darkness. NASA's New Horizons spacecraft flew past Pluto in July 2015 at a distance of about 33 astronomical units from the Sun, revealing a world of nitrogen ice plains, mountain ranges made of water ice, and a thin haze of atmosphere backlit by the distant Sun. The images were stunning, but the communication reality behind them was sobering. The data from the Pluto flyby took over 16 months to transmit back to Earth. Not because the transmission was slow by engineering standards, but because the signal was so faint at that distance that the data rate had to be throttled to roughly 1 to 2 kilobits per second. A single high-resolution image that would download to your phone in a fraction of a second took hours to trickle across 2.8 billion miles of space. New Horizons is still operational, still pushing outward through the Kuiper Belt. Scientists at the Southwest Research Institute are now using solar wind forecasting combined with heliosphere models to predict when the spacecraft will encounter the next great boundary, the termination shock. This is where the story shifts from the weakening of sunlight and the stretching of communication to something more fundamental, the loss of the sun's physical influence on the space around you. The sun does not simply emit light, it emits a wind. The solar wind is a continuous stream of charged particles, mostly protons and electrons, flowing outward from the sun's corona at speeds ranging from roughly 200 to 500 miles per second. This wind carries the sun's magnetic field with it, stretching it outward like an enormous rotating spiral that fills the space between the planets. Everything inside this wind, every planet, every asteroid, every spacecraft, exists within a bubble of solar influence. The solar wind pushes outward in every direction, inflating this bubble against the pressure of the interstellar medium, the thin gas and dust that fills the space between stars. The bubble has a name. It is called the heliosphere, and it is the largest structure the sun creates. The heliosphere is not a simple sphere. It is shaped by its interaction with the interstellar medium, which itself is not stationary. The solar system is moving through the local interstellar medium at roughly 16 miles per second, which compresses the heliosphere on the leading side and stretches it into a long tail on the trailing side. The overall shape is debated. Some models show it as a comet-like structure with a long tail. Others suggest it is more rounded, shaped by the interstellar magnetic field pressing inward. What is not debated is that it has layers, and each layer represents a transition in the physical environment. The first boundary a spacecraft encounters when heading outward is the termination shock. This is the point where the solar wind, which has been flowing outward at supersonic speeds, slams into the resistance of the interstellar medium and abruptly slows down. The wind does not stop here. It slows from supersonic to subsonic, compresses, heats up, and becomes turbulent. Voyager 1 crossed the termination shock in December 2004 at a distance of approximately 94 astronomical units. Voyager 2 crossed it in August 2007 at approximately 84 astronomical units. The difference in distance tells you something important. The termination shock is not a fixed wall. It moves inward and outward in response to changes in solar wind pressure, which varies with the 11-year solar activity cycle. When the sun is active and the solar wind is strong, the shock pushes outward. When the sun is quiet, interstellar pressure pushes the shock inward. The boundary breathes. Beyond the termination shock lies the helios sheath, a turbulent region where the slowed solar wind piles up, compresses, and deflects as it meets the incoming interstellar medium. The helios sheath is thick, extending tens of astronomical units, and it is a chaotic, poorly understood transition zone. The solar wind here is no longer flowing outward in an orderly radial pattern. It is sloshing, eddying, and being deflected sideways as it tries to flow around the obstacle of the interstellar medium pressing inward. Temperatures in the helios sheath can exceed 100,000 Kelvin. Though the gas is so thin that this temperature represents the energy of individual particles, rather than the kind of heat you would feel. A thermometer placed in the helios sheath would not register warmth. It would register the near absolute zero temperature of radiation equilibrium, because there are so few particles that their collective thermal energy is negligible. And then, beyond the helios sheath, lies the heliopause. This is the boundary, the true edge of the sun's domain. The heliopause is where the outward pressure of the solar wind finally balances the inward pressure of the interstellar medium. Beyond it, the solar wind does not flow. The sun's magnetic field no longer dominates. The particles filling space are no longer solar in origin. They come from the galaxy. Voyager 1 crossed the heliopause on August 25, 2012, at a distance of approximately 122 astronomical units from the sun. The evidence was unmistakable. The spacecraft's instruments detected a sharp drop in the intensity of solar wind particles and a simultaneous surge in galactic cosmic rays compared to the helios sheath. The magnetic field changed direction, aligning with the interstellar magnetic field rather than the solar field. Voyager 1 had entered interstellar space, not the space between galaxies, but the space between stars. The local interstellar medium. The ocean beyond the shoreline of the sun's influence. Voyager 2 confirmed the crossing when it passed through the heliopause on November 5, 2018, at approximately 119 astronomical units. Because Voyager 2 still had a functioning plasma science instrument at the time, it provided direct measurements of the interstellar plasma that Voyager 1 could not. The data revealed that the plasma in the local interstellar medium is significantly denser than the plasma inside the heliosphere, confirming theoretical predictions. 5 research papers published simultaneously in Nature Astronomy describe the findings from Voyager 2's 5 operating instruments, painting a detailed picture of the cosmic shoreline where the sun's influence ends and the galactic environment begins. What the Voyagers found beyond the heliopause was not empty space. This is one of the most important corrections to popular understanding that this story can offer. Interstellar space is not a vacuum in the colloquial sense. It is not nothing. The local interstellar medium surrounding our solar system contains approximately 0.3 atoms per cubic centimeter, mostly hydrogen with some helium. That density is extraordinarily low by earthly standards. The air in the room you are sitting in contains roughly 25 quintillion molecules per cubic centimeter. But it is not zero. It is a real, measurable medium with physical properties that matter. The temperature of the local interstellar cloud The specific patch of interstellar material our solar system is currently passing through has been measured at approximately 7,500 Kelvin, plus or minus about 1,300. That sounds searingly hot. But remember that temperature in a gas this thin describes the average energy of individual particles, not the heat you would feel. With only a fraction of an atom per cubic centimeter, there is no meaningful thermal transfer to a surface. A spacecraft in interstellar space would not be scorched by this temperature. It would radiate its own heat into the void and cool toward the cosmic microwave background temperature of approximately 2.7 Kelvin. The interstellar medium is simultaneously thousands of degrees in particle energy and functionally freezing in terms of thermal experience. It is a paradox that only makes sense when you abandon the everyday meaning of temperature and think in terms of physics. The interstellar medium also contains dust. Interstellar dust grains, remnants of ancient stellar explosions and the cool atmospheres of dying giant stars, permeate the space between stars. The Ulysses spacecraft confirmed the presence of interstellar dust particles streaming into the solar system at the distance of Jupiter, moving in a direction opposite to the expected flow of interplanetary dust. These grains are tiny, typically smaller than a micrometer, but they carry information about the chemical history of the galaxy, and they represent a collision hazard for any spacecraft moving at high relative velocities through interstellar space. And then there is the radiation. Beyond the heliopause, galactic cosmic rays are no longer modulated by the solar wind. Inside the heliosphere, the solar wind and its embedded magnetic field partially deflect incoming galactic cosmic rays, reducing their intensity at Earth and throughout the inner solar system. This shielding effect varies with the solar cycle. During solar maximum, when the solar wind is strong and turbulent, cosmic ray intensity inside the heliosphere decreases. During solar minimum, when the wind weakens, more cosmic rays penetrate inward. Beyond the heliopause, this modulation vanishes. The full, unfiltered flux of galactic cosmic rays arrives from every direction. Voyager 1's cosmic ray instrument measured this increase directly, detecting a rise in galactic cosmic ray intensity as the spacecraft crossed into interstellar space and the solar wind's deflecting influence disappeared. As of mid-2026, Voyager 1 is approximately 163 astronomical units from the Sun and approaching a landmark milestone. On November 18, 2026, at 2:16 in the morning Pacific Standard Time, Voyager 1 will become the first human-made object to reach a distance of 1 light day from Earth. 1 light day, 16 billion miles. A distance so great that a radio signal traveling at the speed of light will take a full 24 hours to reach the spacecraft. A command sent on Monday morning will not arrive until Tuesday morning. A reply, if Voyager 1 sends one immediately, will not return to Earth until Wednesday morning. The round-trip communication time will span 48 hours. 2 full days to ask a question and receive an answer from a machine that weighs less than a small car. NASA has calculated this milestone to the precise second. It is not approximate. It is not symbolic. It is a communications fact that defines what operating at this distance actually means. Engineers at the Jet Propulsion Laboratory who manage the Voyager mission must plan every command sequence days in advance. They must anticipate problems they cannot diagnose in real time. They must trust a spacecraft built with 1970s technology, running on a power source that loses approximately 4 watts per year, operating with only 2 functioning science instruments, the magnetometer and the plasma wave subsystem, to execute commands correctly in an environment no human engineer has ever visited or ever will. Meanwhile, NASA's Interstellar Mapping and Acceleration Probe, which launched on September 24, 2025, aboard a SpaceX Falcon 9 rocket, arrived at the Sun-Earth Lagrange Point 1 on January 10, 2026, and began its 2-year primary science mission on February 1st, 2026. This spacecraft carries 10 scientific instruments designed to map the heliosphere from the inside, studying energetic neutral atoms that stream inward from the heliosphere's boundary and carry information about conditions at the termination shock and heliopause. The Interstellar Mapping and Acceleration Probe cannot visit the heliopause itself, but it can observe it remotely by detecting particles that originate there and travel inward to the Lagrange point about 1.5 million kilometers from Earth. The mission represents humanity's latest attempt to understand the boundary that separates the Sun's domain from everything else. And its early observations are already refining our models of the heliosphere's structure. Researchers have found that the heliosphere's termination shock and heliopause surfaces are rippled and oblique, not smooth, with significant asymmetries compared to steady-state models. The boundary is more dynamic, more irregular, and more responsive to solar wind variations than earlier maps suggested. Farther out, New Horizons continues its journey through the Kuiper Belt, heading in a direction that will eventually carry it toward the termination shock. Scientists are using solar wind pressure forecasts to predict when New Horizons will encounter this boundary, potentially providing a third data point from a different direction and a different solar cycle phase to compare with the Voyager crossings. Each new crossing teaches us more about the shape and behavior of the heliosphere. The bubble that protects every planet, every asteroid, every grain of interplanetary dust from the full intensity of the galactic radiation environment. The heliopause is not the edge of the solar system in the gravitational sense. The Sun's gravity extends far beyond it, holding the Oort cloud, a hypothetical shell of trillions of icy bodies, at distances of up to 100,000 astronomical units. Objects in the Oort cloud are gravitationally bound to the Sun, even though they sit well outside the heliosphere, well beyond the reach of the solar wind and fully exposed to the interstellar medium. They orbit in a region where the Sun is nothing more than a slightly brighter star among many, where sunlight is so faint that it contributes essentially nothing to the thermal environment, and where the only reminder that you belong to a stellar system is the gentle gravitational tug that keeps you from drifting away entirely. The Oort cloud is worth pausing on, because it represents a threshold unlike any other in this journey. Everything closer to the Sun exists in some measurable relationship with the star's energy output. Mercury is scorched by it. Earth is warmed by it. Mars is dimly lit by it. Jupiter barely feels it. Neptune can hardly detect it. But even at Neptune, the Sun is doing something. Photons arrive, solar wind flows, the star is present. In the Oort cloud, the Sun does almost nothing. An object orbiting at 50,000 astronomical units receives sunlight that is less than 1/billionth of what Earth receives. At that intensity, the Sun's contribution to the surface temperature of an icy body is less than the contribution from the cosmic microwave background, the residual heat from the Big Bang itself. The oldest light in the universe warms you more than your own star does. You are still gravitationally bound to the Sun. You are still, in the strictest technical sense, part of the solar system. But the Sun has stopped being a sun to you. It is a gravitational address, not a source of energy or protection. You belong to it the way a forgotten parcel belongs to a shipping company. Your name is on the manifest, but no one is coming to deliver you anywhere. Objects in the Oort cloud orbit so slowly, taking millions of years to complete a single circuit, that the gravitational perturbations from passing stars and from the tidal forces of the Milky Way itself can gradually nudge them off course. Some get pushed inward, falling toward the Sun on long eccentric orbits that carry them through the inner solar system as long-period comets. Others get pushed outward, gently liberated from the Sun's gravity entirely, drifting away into interstellar space to become rogue objects orbiting nothing at all. The boundary between belonging to the solar system and not belonging to it is not sharp. It is statistical. It is a probability that decreases with distance, the gravitational grip loosening with every 1,000 astronomical units, until at some point the sun simply cannot hold on anymore, and the object is free. Not free in any dramatic sense, but free in the sense of being abandoned, released into a galaxy that has no use for it and no awareness of its existence. If you could travel to the Oort cloud and look back toward the sun, you would see a star. Not the brightest star in the sky, not obviously special, just a star, one of thousands visible to the naked eye from that vantage point, indistinguishable in brightness from dozens of others. You would have to know which one it was to find it. And the light arriving from it, the ancient sunlight that has been traveling for days or weeks to reach you at this distance, would carry no detectable warmth, no usable energy, no shielding effect, and no information about the planets that orbit closer in. The sun would be a fact in your navigation database, not a presence in your experience. Everything it does for Earth, for Mars, for Jupiter, for Neptune would be irrelevant to you. You would be in the solar system on paper and in the galaxy in practice. But the heliopause, not the Oort cloud, is the edge of the sun's protection. Beyond it, the solar wind is gone. The sun's magnetic field no longer shapes the local environment. Galactic cosmic rays arrive at full strength. The particles surrounding you are interstellar, not solar. The dust grains are forged in the death throes of other stars, not ground from asteroids orbiting your own. The medium you are traveling through has nothing to do with your star, your planets, or your home. You are in the galaxy now, not in the solar system's extension of the galaxy, but in the galaxy itself. Voyager 1 has been operating in this environment for 14 years. It is running on fumes, shutting down instruments one by one to conserve the dwindling power from its radioisotope thermoelectric generators. In April 2026, engineers powered down the low-energy charged particles experiment to save power, hoping to buy time for an ambitious engineering maneuver nicknamed the Big Bang, a coordinated swap of powered systems designed to extend the mission into the early 2030s. Voyager 2 underwent a similar instrument shutdown in March 2025. Both spacecraft are approaching the end of their operational lives, not because they have reached a destination, but because their power sources are decaying, and the cold of interstellar space is slowly overtaking the heaters that keep their systems functional. When Voyager 1 finally goes silent, it will continue moving outward at roughly 11 miles per second relative to the sun. It will not stop. It will not slow down appreciably. It will drift through interstellar space for millions of years, a silent artifact carrying a golden record etched with sounds and images from a planet it will never return to. It will pass within 1.6 light-years of a star in the constellation Camelopardalis in approximately 40,000 years. But it will not stop there either. It will keep going. A piece of Earth's engineering legacy tumbling through the galaxy long after every trace of the civilization that built it has been forgotten. Beyond the heliopause, the sun's protection is gone. The solar wind that inflated the bubbles shielding every planet you have ever known has faded to nothing. The magnetic field that deflected a portion of the galaxy's cosmic radiation has released its grip. The photons that warmed every world from Mercury to Neptune have become so sparse at this distance that they contribute less energy per square meter than the cosmic microwave background. The faint afterglow of the Big Bang itself, the sun is still there. You could still see it if you looked back. But it is no longer doing anything for you. It is not warming you. It is not shielding you. It is not powering your instruments or deflecting particles headed toward your hull. It is a star in your rear view, one among billions, growing dimmer with every passing year. But the truly terrifying realization is not what waits out there in interstellar space. It is what no longer exists behind you. The atmosphere is gone. It has been gone since the launch pad. The magnetic field is gone. It vanished when you left Earth orbit. Rapid communication is gone. It disappeared somewhere around Mars. Practical resupply is gone. It became impossible past Jupiter. Sunlight as a usable energy source is gone. It faded through Saturn and Uranus and guttered out around Neptune. And now the solar wind itself is gone, the last physical emanation of the star that created your world. The last breath of the sun, reaching outward into the darkness, has dissipated into the interstellar medium, and you have crossed the line where it can no longer touch you. Every one of these losses was a threshold. Every one removed something that life on Earth depends on without ever noticing. And the horror is not that the losses are dramatic. The horror is that they are quiet. They happen gradually across billions of kilometers, one system at a time, until you turn around and realize that everything that once kept you alive has been subtracted away. What remains is you, your machine, and the galaxy. Voyager 1 is the farthest human-made object in existence. It has been traveling for nearly 50 years. It has crossed the termination shock, passed through the Helios heath, and punched through the heliopause into interstellar space. It is now approaching 1 light day from Earth. And in all that time, across all those billions of kilometers, it has covered less than 0.003 light years. Let that number settle for a moment. The nearest star system to the Sun, Proxima Centauri, is approximately 4.24 light-years away. Voyager 1, after half a century of continuous travel at roughly 11 miles per second, has completed less than 1,000th of that journey. At its current speed, Voyager 1 would need over 70,000 years to reach Proxima Centauri, if it were even heading in that direction, which it is not. 70,000 years. That is longer than the entire history of anatomically modern humans outside of Africa. Longer than the span from the cave paintings at Lascaux to the first footstep on the moon, repeated 3 times over. Voyager 1 has traveled farther from Earth than anything humanity has ever built, and it has barely left the front porch. This is the scale that interstellar space imposes on every fantasy of deep space travel. The distances are not merely large. They are large in a way that exposes the entire history of human technology as a preliminary exercise. Every rocket engine ever built, every propulsion concept ever funded, every trajectory ever calculated, has produced a cumulative result that amounts to a single footstep at the beginning of a walk that would cross a continent. The interstellar medium does not care about human ambition. It extends in every direction for light years, parsecs, kiloparsecs. And the spacecraft we have sent into it are moving through it at speeds that the medium itself barely notices. But suppose for a moment that you could go faster. Suppose a future propulsion technology, perhaps a light sail accelerated by a ground-based laser array like the one proposed by the Breakthrough Starshot initiative, could push a small probe to 20% of the speed of light. At that velocity, the probe would reach Proxima Centauri in roughly 21 years. That sounds almost reasonable, until you consider what the probe would experience during the journey. 21 years of travel through the interstellar medium at 37,000 miles per second. At that speed, every atom of hydrogen in the interstellar medium becomes a projectile. The medium contains roughly 0.3 atoms per cubic centimeter, almost nothing by earthly standards, but at 20% of light speed, each of those atoms strikes the spacecraft with the energy of a small particle accelerator beam. The cumulative effect of trillions upon trillions of hydrogen atom impacts over 21 years would erode the spacecraft's surface, generate secondary radiation from each impact, and create a constant bombardment that no known material can simply shrug off. The interstellar medium, which seems like empty space to a slowly drifting Voyager probe, becomes a hailstorm at relativistic speeds. And that is just the gas. The dust grains, those micrometer-sized particles forged in the atmospheres of dying stars and scattered through interstellar space by ancient supernovae, become catastrophic at high velocity. A single grain 1 micrometer across, striking a surface at 20% of light speed, delivers the kinetic energy equivalent of a small explosive charge. At lower interstellar travel speeds, the dust is a nuisance. At relativistic speeds, it is a bullet. Every grain is a bullet, and there is no way to see them coming. They are too small to detect at any useful range, too numerous to dodge, and too fast relative to the spacecraft for any reactive shielding system to engage in time. A crude vessel traveling at even a fraction of relativistic speed through interstellar space would need a shielding solution that does not currently exist and that may not be physically possible with any material humans know how to manufacture. This is interstellar space, not the romantic void between the stars that science fiction depicts. Clean and silent and traversable, with a sufficiently powerful engine. It is a real physical medium with real physical properties that impose real constraints on anything trying to move through it quickly. It is thin, yes. Thinner than any vacuum humanity has ever created in a laboratory. But it is not nothing. And at the speeds required to cross interstellar distances in a human lifetime, that thin medium becomes an environment as hostile as any that nature has constructed. Beyond the dust and gas, the radiation environment in interstellar space is the most relentless hazard of all. Inside the heliosphere, the solar wind provides a partial shield against galactic cosmic rays. The sun's magnetic field, carried outward by the solar wind, deflects a measurable fraction of incoming cosmic ray particles, reducing the flux that reaches the inner solar system. This shielding effect varies with the solar cycle, increasing during solar maximum, decreasing during solar minimum. But it is always present to some degree. Step beyond the heliopause, and that shielding vanishes entirely. The full, unmodulated flux of galactic cosmic rays arrives from every direction at all times, at all energies. Galactic cosmic rays are not gentle. They include protons, helium nuclei, and heavier ions accelerated to enormous energies by supernova shock waves, neutron star collisions, and other violent events scattered throughout the Milky Way. Some of these particles carry energies exceeding 10 to the 18th electron volts, millions of times more energetic than anything produced by the most powerful particle accelerators on Earth. A single ion nucleus at these energies can pass through meters of solid shielding and still deposit enough energy along its track to damage biological tissue at the cellular level. There is no practical thickness of any known material that can stop the highest energy galactic cosmic rays. You can reduce the dose. You can attenuate the lower energy particles. But the most energetic fraction will pass through anything you put in front of them, including the walls of a spacecraft, including the body of an astronaut, including the delicate strands of DNA that encode every instruction for keeping a human being alive. Inside the heliosphere, this problem is mitigated, not solved, but mitigated. The solar wind deflects enough cosmic rays that the radiation environment in interplanetary space, while significantly elevated compared to Earth's surface, remains within the range that human biology can tolerate for limited durations. Beyond the heliopause, the mitigation disappears. A spacecraft in interstellar space receives the full galactic cosmic ray flux indefinitely. For a robotic probe like Voyager 1, this is tolerable. Electronics can be radiation hardened. Instruments can be designed to function despite particle impacts. Machines do not get cancer. But for a human crew, unshielded exposure to the full interstellar cosmic ray environment over years or decades would produce cumulative radiation doses that exceed every safety threshold medical science has established. The central nervous system effects alone, cognitive decline, memory impairment, increased risk of neurodegenerative disease, represent a threat that no amount of physical fitness or psychological preparation can overcome. And there is no rescue. This is the fact that transforms every other hazard from a technical challenge into something closer to an existential condition. At the Moon, rescue is days away. At Mars, it is months to years away. At Jupiter, it is essentially impossible with current technology. In interstellar space, rescue is a concept that no longer has meaning. No ship can reach you. No signal can coordinate a response in real time. No supply depot exists between the stars. If your life support fails, if your radiation shielding degrades, if your propulsion system malfunctions, if your food production falters, if your water recycling breaks down, if any one of the hundreds of interdependent systems that keep a human being alive in a sealed vessel stops working, you die. Not because the failure is necessarily fatal on its own, but because there is no backup. There is no external system to compensate. There is no neighbor to borrow from, no emergency service to call, no infrastructure of any kind between you and the next star. You are sustained entirely by what you carry and what you can repair. The machine is everything. If the machine works, you live. If it does not, you do not. There is no third option. Now extend this logic further. Past interstellar space, past the local neighborhood of stars, into the true deep between galaxies. The Milky Way is roughly 100,000 light-years across. Beyond its edges, beyond the halo of ancient stars and globular clusters that orbit the galactic center, lies intergalactic space. The nearest major galaxy, Andromeda, is approximately 2.5 million light-years away. The local group of galaxies, the gravitational family that includes the Milky Way, Andromeda, and several dozen smaller companions, spans roughly 10 million light-years. Beyond the local group, the next major structures are galaxy clusters, separated by tens of millions of light-years of almost perfectly empty void. Intergalactic space is the emptiest environment in the known universe. The density of matter between galaxies drops to approximately 1 atom per cubic meter. Not per cubic centimeter, as in the interstellar medium, per cubic meter. To grasp how empty that is, imagine a cathedral, an enormous vaulted space capable of seating thousands. Now remove everything from it, every pew, every pillar, every molecule of air. Fill it with perfect vacuum. In a volume that large, intergalactic space would contain, on average, a single atom. One hydrogen atom drifting alone in a space larger than most buildings you have ever entered. The temperature in these voids hovers near the cosmic microwave background floor, approximately 2.7 Kelvin, barely above absolute zero. There is no light source nearby, no star close enough to warm or illuminate anything, no dust to scatter photons, no structure of any kind for millions of light-years in every direction. No human will travel through intergalactic space. It is important to state this not as pessimism, but as physics. The energy required to accelerate even a small spacecraft to a velocity that could cross intergalactic distances in less than millions of years exceeds the total energy output of the Sun over its entire lifetime. The engineering challenges of maintaining a sealed biosphere for millions of years are not challenges at all. They are impossibilities dressed in the language of speculation. Intergalactic space is not a destination. It is a boundary condition. It is the place where the logic of this entire journey, the progressive removal of protection and support, reaches its conclusion. And that conclusion is not a monster. It is not a threat hiding in the darkness between galaxies. It is not a wall of fire or a region of crushing gravity or a predator lurking in the void. The conclusion is absence. Pure, layered, systematic absence. Every protection that makes human survival possible is stripped away in stages as you move outward from the surface of the Earth. And intergalactic space is simply the final stage, the place where every layer has been removed and nothing remains except the laws of physics and whatever you brought with you. Think about what has been taken from you, layer by layer, threshold by threshold, across this entire journey. You left the surface and lost the atmosphere. That blanket of nitrogen and oxygen that filters ultraviolet radiation, burns up incoming debris, maintains pressure against the vacuum, and carries sound so that you can hear another person speak. All gone the moment you crossed the boundary of space. You climbed past low Earth orbit and lost the magnetosphere, the invisible architecture of magnetic field lines that deflect solar storms and cosmic rays. The shield you never saw and never thought about. Gone once you passed beyond the Van Allen belts. You traveled to the moon and lost rapid communication and rapid rescue. The ability to call home and hear a response in seconds. The knowledge that a spacecraft could reach you in hours if something went wrong, both diminished to the point of irrelevance. You pushed outward to Mars and lost real-time conversation with Earth entirely. You lost the ability to receive emergency guidance fast enough to matter. You lost the psychological comfort of knowing that someone on the ground could help you make a decision in the moment it needed to be made. You traveled to Jupiter and lost solar power as a practical energy source. You lost any meaningful possibility of resupply. You lost the engineering margin that comes from operating within reach of Earth's industrial capacity. Every broken component became a crisis rather than an inconvenience, because the nearest replacement was years and billions of kilometers away. You continued outward past Saturn, Uranus, and Neptune. The sun became a point of light that no longer warmed you, no longer powered you, and no longer dominated the sky. Sunlight, the most fundamental energy source that life on Earth has ever known, faded to irrelevance. The star that drives photosynthesis, that governs climate, that anchors every food chain and every ecosystem on the planet you came from, became indistinguishable from the stars around it in terms of the energy it delivered to your hull. You crossed the termination shock and entered the Helios heath, where the solar wind lost its supersonic authority and began to falter against the pressure of the galaxy pressing inward. And then you crossed the heliopause, and the last physical emanation of the sun, the stream of charged particles that had accompanied you since you left Earth, was gone. Each of these losses was quiet. None of them announced themselves with alarms or explosions. The atmosphere did not slam shut behind you. The magnetic field did not snap like a cable. The communication delay did not arrive all at once. The sunlight did not switch off. Each protection faded gradually, and each fading was so smooth that you might not have noticed the moment it became critical. That is what makes this progression so unsettling. The universe does not warn you when you cross a threshold. It does not tell you that you have just lost something you will need. It simply removes it silently, incrementally, and waits for you to discover the absence on the day you reach for it and find it gone. This is why deeper space is not the same as farther space. Farther implies a single axis, a linear measurement, a number that grows. Deeper implies layers. It implies that the space you are entering is qualitatively different from the space you left behind. Not just more distant, but differently configured, differently provisioned, differently hostile. Every zone outward from Earth is deeper in the sense that it has removed another system of protection. Low Earth orbit is deep compared to the surface because you have lost the atmosphere. Cislunar space is deeper because you have lost the magnetosphere. Interplanetary space is deeper because you have lost rapid communication, practical resupply, and eventually solar power. The outer solar system is deeper because you have lost meaningful sunlight and any realistic hope of rescue. Interstellar space is deeper because you have lost the solar wind and the heliosphere's partial cosmic ray shielding. Intergalactic space is deeper because you have lost even the structure of a galaxy. The density of stars, the gravitational neighborhood that provides reference and context, and the faintest possibility that some other civilization might notice your passage. And the machine dependence grows at every stage. On Earth's surface, you survive by breathing. The atmosphere does the work. In low Earth orbit, a life support system does the work the atmosphere used to do. But Earth is close enough to fix problems quickly. At Mars, the life support system must work for years without resupply, and the crew must be capable of repairing it without real-time guidance from Earth. At Jupiter and beyond, the life support system must work indefinitely. The crew must repair it with only the tools and spare parts they packed before departure. And every failure mode must have been anticipated before launch. Because there is no one to consult when the unanticipated happens. In interstellar space, the machine is not a tool you are using. It is the environment you are living inside. It is the atmosphere, the magnetosphere, the sunlight, the gravity, the food supply, the water cycle, and the communication network. It is every system that Earth provides naturally, replicated artificially in a volume smaller than a house, sustained by engineering that cannot fail because failure is death and help does not exist. This is the core truth that this entire journey has been building toward. The deeper you go into space, the more the universe removes the systems that make survival feel normal. Not all at once, not dramatically, in layers. Earth's atmosphere shields you from radiation, maintains pressure, filters light, and carries sound. Gone at the launch pad. Earth's magnetic field deflects charged particles and protects electronics. Gone past low orbit. Communication with home allows real-time coordination, emotional support, and expert guidance. Gone at Mars. Solar energy powers equipment, warms surfaces, and drives the chemistry of life. Gone past Jupiter. The solar wind creates a bubble that attenuates galactic cosmic rays. Gone past the heliopause. Nearby stars provide gravitational structure, navigation reference, and the theoretical possibility of reaching another system. Gone in intergalactic space. What becomes horrifying is not one monster waiting in deep space. There is no monster. There is no alien predator, no anomalous energy field, no cosmic wall of destruction. The horror is structural. It is architectural. It is the realization that the universe was never built to support you, that Earth was the exception, that the conditions you evolved in were a local pocket of improbable hospitality in a cosmos that defaults to emptiness, radiation, cold, and silence. Every step outward from that pocket makes survival more artificial, more dependent on machines, more fragile, more contingent on every system working correctly all the time, with no margin for error and no external support. Deep space is not one place. It is a series of thresholds where survival becomes more artificial with every step outward. The atmosphere goes first, then the magnetic field, then the speed of communication, then the possibility of rescue, then the warmth and energy of the sun, then the protective wind of the sun, then the structure of a stellar neighborhood, then the structure of a galaxy. Each loss is permanent. Each loss makes you more alone. Each loss shifts the burden of survival from the natural world that created you to the machines you built to replace it. And at the end of this progression, when every natural protection has been subtracted, when every invisible system that kept you alive without your noticing has been removed, what remains is not darkness or danger or some final dramatic revelation. What remains is absence. The absence of warmth, the absence of shielding, the absence of communication, the absence of rescue, the absence of sunlight, the absence of repair, the absence of certainty, the absence of forgiveness. Deep space is the progressive erasure of home, and the deeper you go, the less of home is left. Voyager 1 is still out there, still drifting, still sending its faint whisper back toward a planet it left half a century ago. Soon it will go silent, not because interstellar space will destroy it, but because the small piece of home it carried, the plutonium that warmed its circuits, the electricity that powered its transmitter, the engineering margin that kept it functional far beyond any reasonable expectation, will finally be spent. And when it goes quiet, it will continue outward. Not toward anything, not away from anything, simply outward through the absence, carrying a golden record that no one in the universe may ever play, bearing a message from a species that looked up at the night sky and wondered what was out there, and then built a machine small enough to fit in a living room and brave enough to go find out. The answer to what is out there is not a single revelation. It is a gradient. It is a slow, relentless subtraction of everything that makes life possible, replaced by nothing except distance and silence and the cold light of stars that do not belong to you. That is what deeper means. Not farther, but deeper into a universe that was never yours to begin with, that tolerates your presence only as long as your machines keep running. And that will continue, vast and indifferent, long after the last machine from Earth has gone dark. Right now, somewhere above your head, an invisible shield is keeping you alive. Earth's magnetic field stretches 40,000 miles into space, turning aside a relentless storm of radiation that would tear apart your DNA within hours. Step beyond it, and you enter a universe that begins dismantling every system your body depends on, not all at once, but in layers. First, the atmosphere disappears.